Hello students, welcome to the next lecture on these conventional manufacturing processes, and in this lecture we will discuss about merchant circle diagram. So to understand the merchant circle diagram, first of all let us understand different forces acting during machining operations. So we know that over here, as if we indicate this as the workpiece and this one is the tool. Okay, now what happens is, during machining operation, this chip is flowing upward from the tool, and due to the rubbing action between the tool and this chip, the frictional force is generated, and we know that the frictional force is always in the opposite direction. So we can indicate over here the frictional force in the opposite direction, and the force acting normal to the frictional force, that is indicated as the N. Now similarly, we know that to perform the machining operation, shearing action is required because chip removal is taking place due to the shearing action, right? So at this plane, as the chip gets removed from this particular plane, we know that the shearing force is acting in this particular direction. So this force acting to remove the chip using the shearing action, it is indicated as the shear force Fs. And similarly, the force acting in the normal direction, that is the shear force normal to this direction, it is indicated as the Fsn. So these are the main four forces that are acting during the actual machining process. And we know that as this process is continuously working in the dynamic environment, these forces are not possible to measure. So to obtain the relationship, what we can do is we can theoretically resolve these forces in the horizontal and vertical direction. So if we see, we can resolve this force as F is acting in this direction. We can resolve this force F in vertical direction and in horizontal direction. So similarly, all the four forces can be resolved in the vertical and horizontal directions. So by resolving all these forces in these two directions, we will get the algebraic sum of all the possible forces that are acting during the machining process. And these forces are indicated as, the first one is Fh, that is the horizontal force, summation of all the horizontal forces acting, and the second one, that is the vertical force. And this, in further discussion, we will indicate this horizontal force as the thrust force, because this force helps to overcome the thrust. Similarly, this vertical force is helpful to remove the material or to perform the cutting operation, and that's why we will indicate this force as the cutting force. So these Fh and Fv now is replaced by these two terms, that is the thrust force and the cutting force. And how we have obtained these two forces? We have obtained these two forces by resolving in horizontal and vertical direction. And that's why in many of the cases, these two forces are indicated as the resolved forces. So I hope now you have the clarity which type of the forces are acting during machining operations. So we know that all these forces are acting during the actual working condition, and these forces are not possible to measure. And these forces, as we have discussed, these are acting in the mutually perpendicular direction, and these resolved forces can be measured using the dynamometer and the spring balance. But now we know that for calculation purpose, the actual forces are required, and we are not able to measure that actual forces. So to obtain the relationship between these actual forces and the measurable forces, one another method is available, and that method of obtaining the relationship between these measurable and actual forces, that method is called as the merchant circle diagram. And in the case of merchant circle diagram, what we are doing is, we know that now we have the value of the thrust force, right? And we also have the cutting force. Now, so from these two horizontal and vertical forces, we can get the resultant value. And this resultant value we know easily with the help of the parallelogram law. These R we will get by using this equation, R is equal to under root FC square plus FT square. And here these R, These R indicates the diameter of the merchant circle diagram. So clearly understand these. This R is not the radius, it is indicating the resultant force, and this one is the diameter of the merchant circle diagram. So we will use these as the base and we will move forward to understand the merchant circle diagram. Now to draw the merchant circle diagram, there are certain assumptions and these assumptions are mentioned over here. Some of them are, as you can see over here, during machining, we know that, now we know this diagram, right? And the chip removal takes place in this particular direction, means the shearing force is acting in upward direction only. So we are assuming that this shear force always acts in the upward direction only. Then the width of this chip, the actual width, and after removal the chip width also remains constant. So we are making this type of certain assumptions which is mentioned over here. You can read the certain assumptions that are mentioned over here, and then onward we are moving to understand the actual representation of the merchant circle diagram. So this is the merchant circle diagram that you will be drawing. But now how this diagram is drawn? So for that it is very easy to understand. You just needed to understand the basic process. See over here. Okay, we know the chip removal process, right? This one is the workpiece, and over here one tool is available to remove the material. Now this tool makes certain angle with the perpendicular, and we know that this angle is the back rack angle. So first angle that is important to us, that is the back rack angle. Now we know that as this chip is moving in upward direction, so what happens, the frictional force will act in the opposite direction, that is F. Similarly, perpendicular to this or over here at the angle of approximately 45 degree, what happens, the shearing plane is cut off, or the shearing action helps to remove the chip or remove the material from the workpiece, and the force acting in this direction, we know that it is indicated as the shearing force that we have understood. So as you can see over here, now first start from any particular point, and now when you put the tool over here, now we know that first the frictional force that is acting in the downward direction. So we are drawing the frictional force in the downward direction as shown over here, and we know that as this tool makes the angle alpha with the perpendicular direction, and with the law of mathematics we know that if this angle is alpha, then similarly this angle can also be indicated as the alpha. Now the force normal to the frictional force is drawn over here, right? So first two lines how we have drawn, that you can understand. Similarly, from this point we know that the shearing force is acting in upward direction. So here we have drawn the shearing force F as that you can see, and we know that this shearing force makes certain angle with this parallel, and this angle is indicated as the phi, and this is nothing but the shearing angle. So here the shearing angle phi is indicated. Similarly, the normal force to the shear force, it is indicated as the FSN, it is drawn over here, and these both forces touches at this particular point. Now from the starting point and to the intersection point, we are joining them using one particular line, and this line is giving us nothing but the resultant force, that is R, right? So now last we know that thrust force is the summation of all the forces, that is the horizontal force, and the cutting force, that is the summation of all vertical forces, that is the FC. Or so these two are indicated over here, as you can see from this point. This first vertical force is this horizontal force is indicated over here, and this one is nothing but the cutting force. And similarly the another force acting in the vertical direction, that is indicated as the FT. So just correct this, these two forces, this FT will act in vertical direction and this FC will act in the horizontal direction. Why? because we know that the cutting is taking place in this direction. As we are moving forward in this particular direction, then and then only cutting is happening, and that's why we are indicating as the cutting force Fc. So now I hope you have the clarity about the forces that are indicated over here in this particular diagram. So the indication of your diagram is complete. Now you have to understand the angles represented over here. So for that, as you can see over here, how this angle alpha is indicated, that we know now very well. From the angle of this particular point, using the mathematical law, we have indicated the angle alpha over here. Similarly, with the parallel line, the shear force makes certain angle and it is indicated as the shear angle. Now, as you can see, this one is the frictional force. This one is the frictional force, and the force is acting in the normal direction, that is the n. Now these two makes also certain angle, and this is the right angle triangle. So the angle made between these two at these two particular point, it is indicated as the beta. Beta is nothing but the friction angle. So this beta is indicated over here. Beta is the friction angle, and we know this is the right angle triangle, and hence it is indicated as the 90 minus beta. So this angle is also indicated over here, right? Now we know that, as you can see over here, this angle is the right angle triangle. So now to get this angle over here, we do not know this angle. So to get that, what we will do, we will just equate with the original equation, means 90 degree, that is equal to what? 90 minus beta plus alpha plus certain angle theta that we do not know. So this theta will give us what? This 90 will cancel out, and this theta will give us the value of beta minus alpha. So this angle beta minus alpha is indicated over here. Okay, so all the necessary forces and all the necessary angles are indicated over here, and this entire diagram is known as the merchant circle diagram. So now we know that in these two combination of forces are available: actual forces, that is the F, N, Fs and Ns. All these forces are also available, and the two measurable forces, that is the cutting force and the thrust force, these two forces are also available. So now using this particular diagram, we can compare the measurable forces and actual forces, and we can get exactly the data required for our particular machining operations. So these are the notations that we have used in our overall diagram, so you can go through this. Now from this diagram we can get certain relationship. Now how we can get this relationship? Just you need to go through these three triangles that are happening in this diagram. So as you can see, the first diagram, see over here, if this point is A, this point is B, and this is the point C. So this ABC is the right angle triangle, being the right angle at the point B. So this resultant force R is common to all the three triangles. Now as you can see, for the first triangle ABC, if we write the equation from this particular angle using the sine and cosine rule, what we can write is, if we write sine beta, that is equal to, we know that the angle that is at the, the dimension at the point AB, at the line AB, that is the force F, divided by the hypotenuse, that is the R. Similarly, if we write the equation for cos beta, so for cos beta we have the equation that is the BC divided by AC, and this will give us what? It will give us N divided by R, and in these two equations we know that the common term is resultant force R. So if we get the resultant force as the main variable, so what we will get? We will get this first equation, R is equal to F divided by sine beta, that is equal to N divided by cos beta, right? Now next, for the second triangle, consider this second triangle 2, which is indicated over here. So just a second. Okay, so now for this another triangle, and now let us indicate this as the point D. Now for the triangle ADC and this D, at the point D the right angle is available. So now similarly, if we write the equation for this angle beta minus alpha, if we write for sine beta minus alpha, we will get that sine beta minus alpha will give us what? It will give us DC divided by AD. So that will give us FT divided by R. And similarly, we can write for the cos beta minus alpha, and this will give us what? FC divided by R. So similarly, if we get the common term R over here, we will get the second equation, R is equal to FC divided by cos beta minus alpha and FT divided by sin beta minus alpha. And similarly, for the triangle 3, for this third triangle, consider the triangle A, C, and let us indicate this point as the E. So for the triangle AEC, where the E point indicates the right angle triangle. So now here, what will be the angle? This entire will give us the angle, and this entire angle is nothing but the phi plus beta minus alpha, right? So this phi plus beta minus alpha, similarly we will use the cos and sine rules. So as we use the cos rule for this particular angle, for the cos rule, what we will get? Cos phi plus beta minus alpha, that is equal to what? It will give us Fs divided by R. And similarly, if we use sine, then sine phi plus beta minus alpha, that is equal to Fsn divided by R. And now if we get the common value R, so we will get this third equation, R is equal to Fs divided by cos phi plus beta minus alpha equal to the second term that is indicated over here. So these are the three equations which will be helpful to get the relation between all the available measurable and actual forces. So I hope now you have the clarity how to get these three equations from the given diagram. Right. Now using the second equation, by comparing these 2 points, equation 1 and equation 2, we can get the another relation that you can see over here. If we compare that two equation, what we will get now, as you can see over here, first write FC cos beta minus alpha, that is equal to, as you can see over here, what is indicated? That is Ft sine beta minus alpha. So now if we interchange these positions, what we will get? We will get tan beta minus alpha, that is equal to Ft divided by Fc. And now if we use tan inverse, what we will get? Beta minus alpha tan inverse Ft divided by Fc. And from this equation we will get the relation for friction angle, backrack angle, thrust force and the cutting force. So we will get the equation beta is equal to alpha plus tan inverse Ft divided by Fc. And this Ft divided by Fc, this is the ratio of thrust force to the cutting force. And this friction angle beta is also indicated as the beta equal to tan inverse mu, whereas mu is nothing but the coefficient of friction. And now we can similarly from all these relations we can also get the value of the shear angle phi, and we can get the value of the shear angle phi by using the equation that we have derived from the chip thickness ratio, and this equation is tan phi equal to r cos alpha divided by 1 minus r sin alpha. Now if we have known value of the alpha, that is the backrake angle, then we can easily get the value of the shear angle, that is the phi. So I hope now you have understand the different relations that we can use to get the relationship between f and fs, ns, ft, fc, and the three angles, that is phi, beta and alpha. So using this diagram you can get the relationship between all these variables that are involved during the machining operation. Now what happens in most of the cases, the cutting force is greater than the thrust force, but there are certain machining operations in which what happens, this thrust force is greater than the cutting force, and due to these particular reasons the ratio of thrust force to cutting force is getting higher, or it is getting greater than 1. So if we take the example for the grinding, the ratio is approximately near about 2.5, and we know that this ft divided by fc. So from these ratio what we will understand is, and we also know the relation of beta tan inverse mu, and so due to the ratio of ft greater than fc, what happens, the angle beta becomes greater than 45, and if the angle beta is greater than 45, we are getting the value of mu greater than 1. That means the coefficient of friction, its value is getting, we are getting the value of coefficient of friction higher than 1, and which is not desirable, because we know that the value of coefficient of friction always remain between 0 to 1. That means in such cases where the thrust force is greater than cutting force, in this type of cases we cannot use the basic theorem, and for this type of cases we need to use the classical friction theorem. From that we need to find the coefficient of friction. So what is this theorem? So this theorem indicates that when the value of beta is greater than 45 degree, in this case you will find the value of mu using the equation given over here, that is logarithmic of 1 divided by r divided by pi by 2 minus alpha. Here these r indicates the chip thickness ratio, alpha is the rake angle, and you need to understand that this rake angle you need to use in the radians. You cannot use the rake angle in the form of degrees. First you need to convert it into the radian, and then only you can use this value of alpha to get the value of coefficient of friction. So this is one of the special case that you need to understand. In certain cases you need to find the value of mu. So when the case is such as the grinding, when the value of coefficient of friction is getting greater than higher, or the greater than the permissible limit, that is 1, in such cases you need to use the classical friction theorem, which is indicated over here. So this is the overall details about the merchant circle diagram and the relations that you can get by drawing this particular diagram. Now there is one special case of the merchant circle diagram. So what is the special case? We have drawn that in this case what we are assuming, or we are considering that this tool is at a certain angle with the particular perpendicular direction, and this angle is the backrake angle. But there are certain cases where this tool is straight, means in the orthogonal direction at the 90 degree as shown over here. So in such cases what happens, the value of alpha becomes 0 degree, and so such cases, now we know that as the chip is flowing in this direction, we will get the frictional force in the downward direction, and the force normal to the frictional force, it is indicated over here as the M. Now second is common, this shear force Fs, it is in the direction over here due to the shearing plane, and these two are the common terms, that is Fs and Fsm. Similarly, we know these two horizontal and vertical forces. This horizontal force gives us the cutting force, and the vertical force gives us the thrust force. But what is the main important logic that you need to understand? So in such cases where the alpha is 0 degree, you do not need to understand, you do not need to go for a particular equation. You will get the clarity that here the thrust force will give us the value of the frictional force, and this cutting force will give us the value of the normal force to the frictional force, because this F and the thrust force will remain same. Similarly, this cutting force and the force normal to the frictional force, these will also remain the same. So this is one of the special case when the alpha is 0 degree, you will directly get the knowledge that this thrust force will give us the value of the frictional force and the cutting force will give us the value of the normal force to the frictional force. So what are the advantages of using this merchant circle diagram? So we know that we can easily get the relationship between the actual forces and the measurable forces. So that is one of the first advantage. Then using this diagram, we will get the value of the friction, or we will get the coefficient of friction also using this equation or using this relationship. And as we have the relationship between all the different variables involved during the machining operation, we can easily get the relationship between all the variables involved. So these are the advantages of merchant circle diagram. Now, what are the limitations of merchant circle diagram? So the major limitation of this diagram, that is, it is only applicable to the orthogonal cutting processes. It is not applicable to the oblique cutting processes. Second, the value of coefficient of friction that we are getting, that are not the exact, because we are using one theoretical approach or diagrammatical approach where we are trying to resolve the forces and get the value. So we are not getting the exact value, but we are getting the apparent values. And second, last one, that is, it is based on the single plane theory. Means we are using only one pen and paper, and on the plane of paper we are drawing these formulations, and we know that the machining process is happening in the 3D environment. So there might be a certain chances that we are assuming certain points, and we know that we have assumed certain things. So we are not getting the exact values of the forces involved during the machining operations. But we can get the idea about the different forces acting, and we can get the approximate values that are involved during machining operations. So these are the limitations of the merchant circle theory. So I hope you got the clarity about in detail merchant circle diagram, its advantages and limitation, and how to derive the relationship between the measurable and actual forces. So looking forward to see you all in our next lecture. Up to then, thank you.